Okay, so this is the second lecture over chapter 15. So in this lecture, we look at the different reactions that dienes undergo, and we'll look at some more examples of reactions at the allylic position. So if you take a diene and react it with HBr, then you make two different products. So this one's what's called the 1,2 addition product, and this one's called the 1,4 addition product. So with dienes, you'll always get at least two products, and as we'll see in another example, you'll get four different products. And then we'll want to look at which one of those is the major product depending on the conditions of the reaction. So this is the mechanism we've seen in the previous semester in Organic 1 when we looked at Chapter 8, how alkenes react with HBr. So we can take the two electrons in the double bond, make a bond of hydrogen, right, and then we'd have a Br minus. So that would give you this carbocation, which is primary, and then a Br minus could attack this carbon, and then that would give you this as a possible product. Or if H adds to, so let's call this carbon 1, 2, 3, and 4. Or if hydrogen adds to carbon number 2, so if we take the electrons and make a bond of hydrogen this way, and then Br minus leaves. So now we have a secondary and allylic carbocation, and then Br minus would attack to give this as a possible product. So if this alkene reacts, which carbocation are you going to make? Primary or secondary and allylic? And of course the answer is secondary and allylic, so this is not going to happen to any substantial amount, so we can ignore that for all practical purposes. And only the secondary and allylic carbocation in this case is the one that matters. And of course this is following the Markov-Nikov addition. You put the hydrogen on the carbon with the most number of hydrogens, and then Br minus added to the other carbon. And so this makes what's called the 1,2 addition product, because if we call that 1, 2, 3, and 4, we put the hydrogen on carbon 1 and we put the bromine on carbon 2 with respect to each other. So it's not a nomenclature thing, it's where the two groups added with respect to each other, 1 and 2. But since you have an allylic carbocation, then there's always a possibility of resonant structures, right? So I drew the carbocation here again, and if you drew the resonant structure, if you remember how to do that, you can move the double bond over to satisfy the octet rule in the carbocation, and then that would leave this carbon electron deficient, and so now you have a primary and the allylic carbocation, and then the Br minus could attack there. And now you have what's called the 1,4 addition product, since hydrogen went to carbon 1 of the double bond and bromine went to carbon 4 of the double bond. All right, so H and Br are said to have done 1,4 addition here, and in the product above it, they are said to have done 1,2 addition. Okay, so which is the more stable, or which is the major product? Well, that actually depends on the conditions, right? Because in the 1,2 addition product, it's got the more stable carbocation intermediate, but in the 1,4 addition product, it's got the more stable alkene, because that alkene is disubstituted, whereas in the 1,2 addition product, right, that alkene is monosubstituted. So it's more important. Is the carbocation stability more important, or is the alkene stability more important? Well, that depends on the temperature. So if you do this reaction at -80, so let's just say you did it at cold temperature, then you get an 80% yield of the 1,2 addition product and a 20% yield of the 1,4 addition product. Whereas if you did that reaction at a warmer temperature, in this particular case, if you did it at 40 degrees, then you only get 15% of this, and you get 85% of that. Okay, so basically for these reactions, you always have a kinetic product and a thermodynamic product. The kinetic product is the one that's favored at low temperature, and it's going to arise from the more stable carbocation intermediate. And the thermodynamic product is going to be the one that's favored at high temp, and it's going to arise from the more stable alkene product. So why does this happen? Let's see, so if you make this carbocation, and then that leads to product, versus the other carbocation, and then that leads to product. Well, so this is basically what the energy well looks like if you sketch the energy well for this reaction, or the reaction coordinate diagram. Right, the secondary analytic carbocation is more stable than the primary analytic carbocation. So this pathway is faster, which means you can make more of this at low temperature, but all reactions are reversible. And but this is less stable. The product is less stable because the alkene is monosubstituted, whereas this alkene is more stable because it's disubstituted. So since reactions are reversible, so it can go over the small energy barrier to make the monosubstituted alkene, but then that can go backwards and it can remake the diene, well, it can remake the carbocation, and then that has a resonance form that's less stable. So the alkene going that pathway is going to be slower, but then it leads to a deeper energy well. And so once the more substituted alkene is formed, it's more stable, and so it's harder to go backwards. So basically at low temperature, the reaction goes this way, and there's not enough energy to go backwards, so it gets stuck down there, and you make more of the less substituted alkene as the major product because the carbocation intermediate was more stable, and that pathway had a lower energy barrier going forward. But at high temperature, there's enough energy to go backwards, and then it gets down into this energy well where you make the more substituted alkene, and now because that's so much more stable, it can't go backwards, and so now that product tends to accumulate. So it all depends on which temperature you do the reaction at, which of the alkene products is going to be the one that accumulates the most. Okay, so let's take another example. So if we took this diene, so now we have two different alkenes, so we'll call that alkene B and that alkene A. So which one HCl reacts with gives you different products, right? In the first example, it didn't matter because the two alkenes are symmetric, so it didn't matter which one we reacted with, we would get the same products. But in this case, that's not true. So let's let it react with A first. So again, we could add the hydrogen to this carbon, or we could add the hydrogen to that carbon. And so that's what these first two pathways illustrate. So we could move the electrons this way, make a bond to H+, and that would lead to this carbocation, which is secondary allylic. Right? Or we could move the hot electrons this way and make a bond to hydrogen, and then that would lead to carbocation B, which is just primary. So, which is more stable? Secondary allylic is a lot more stable, so we don't even need to worry about carbocation A. So hydrogen is going to add, so the double bond, let's call this 1, 2, 3, 4. So hydrogen is going to go to carbon 1 to lead to the secondary allylic carbocation, and we don't need to consider the other possibility. So now for alkene B, so again, we could move the electrons this way and make a bond to hydrogen, and that would lead to carbocation C. Or we could move the electrons this way and make a bond to hydrogen, and that would lead to carbocation D. So C is tertiary and allylic, and D is just secondary, and tertiary and allylic is way more stable than secondary, so we don't even need to consider D. Right, so if alkene B reacts, we get carbocation C. If alkene A reacts, we get carbocation A. So I've took them and drew them here again, because now we want to consider the resonance form of both of them. So A, if you carbocation A, if you draw a resonance structure, we would move the double bond over here. So now the double bond is there, and the carbocation is there, and that is secondary and allylic. This is secondary and allylic. And for carbocation C, we would take the double bond and move it here. And the carbocation goes there. So this is tertiary and allylic, and this is primary and allylic. Okay, so now we want to put the Cl on each of the carbocations. So the Cl minus, right, could attack that carbon before you drew the resonance structure. So you could have made that product. Or once you drew the resonance structure, then you could have had the Cl there. And you could have made that product. Or for carbocation C, you could have added the carbocation to that tertiary center. And that would have been your product. Or after you drew the resonance structure, you could have had the chlorine here. And that would be your product. So that's your 4 different products. So this would be a 1,2 addition product. This would be a 1,4. So that's the 1,2 and 1,4 with respect to alkene A reacting. Or if alkene B reacted first, this would have been a 1,2 product, and that would have been a 1,4 addition product. Okay, so now which one is kinetic, which one is thermodynamic? Well, so of these 4 carbocations, which one is most stable? Is C. So that's going to be the reaction favored at low temperature. That's the kinetic product. So the lower you do this temperature for this reaction at, the more of that product you're going to make. And the thermodynamic, is going to be the most stable alkene. So for this one, this is a tri-substituted alkene. This is a mono-substituted alkene. This is a tri-substituted alkene, and this is a tri-substituted alkene. But if you remember, alkenes inside the double bond are more stable than alkenes external to the, alkenes inside a ring are more stable than alkenes external to a ring. So this would be the most stable alkene. So let's just call this, so we'll call this 1, 2, 3, and 4. So the thermodynamic product is 1, and the kinetic product is 3. So the lower you do this reaction at, the more 3 you're going to make. The higher the temperature you do this reaction at, the more compound 1 you're going to make. Okay, so same reaction with Br2. If you add bromine Br2 to a double bond, if you remember, you can add bromine and bromine across a double bond. So you could have made that a 1,2 addition product. Or you can make 1,4 addition products as well, just like with HBr or HCl. And in which case, that would be the 1,4 addition product. But in terms of kinetic and thermodynamic product, I'm only gonna ask you in the context of this reaction, and a diene with HCl or a diene with HBr. Okay, and then so we've talked about the reactivity at the allylic position again. So if you remember, if you take an alkene with Br2 and light, this is free radical, which means at some point in the mechanism you would make that radical, and then of course it has a resonance structure. So if you did this free radical bromination, you would make that as a possible product, and that as a possible product. And then this would be the major product based on what we've done in the past, based on stabilities of free radicals. Because the tertiary, this is secondary allylic, and this is primary allylic, and so the secondary allylic radical is going to lead to the more stable major product. Okay, so the point here though is that since you have Br2, well, Br2 can do other reactions with alkenes, right? It can add do an anti-addition of bromine and bromine across a double bond. Or in this reaction, if you recall, one of the side products is HBr. So the HBr side product could do a Markovnikov addition of HBr across the double bond, so you have those potential side products in this reaction. So if you wanted to try to maximize the yields of these kind of products and avoid the anti-addition of Br2 or the Markovnikov addition of HBr, then you can use a different reagent for this reaction, and that reagent is what's called NBS, where carbon tetrachloride is a solvent, and still you need lighter heat to get this reaction going. So this is NBS. It's just an acronym for N-bromosuccinimide. So basically this is just going to do a free radical. Free radical bromination. Whenever you see it, you can just think about it as a Br2 and lighter heat. It's going to do the exact same thing. It's kind of a neat reaction because the NBS is not very soluble in carbon tetrachloride, and it's more dense because of the bromine. And so basically it's mostly undissolved at the bottom of the flask. And then as the reaction occurs, NBS is converted into this compound succinimide. And that is not soluble in carbon tetrachloride, but it's less dense, so that ends up floating on the reaction. So basically when you know the reaction is done, when there's no more solid on the bottom and you just have solid floating on the top. Okay, so how does this reaction work? So NBS reacts with HBr to make succinimide, a side product in the reaction, but it makes a very small concentration of Br2 that's continually produced during the reaction. So you don't have to worry about Br2 being in high concentration, because if it's in high concentration, then you can do the Br-Br addition across a double bond, and we want to minimize that. So it just produces a small local concentration of Br2, and as soon as the Br2 is forms, it reacts in a free radical bromination. So the basic mechanism for the reaction, so HBr reacts with NBS, so take the two electrons, make a bond from bromine to bromine, and these two electrons become a lone pair of nitrogen, and now you've made Br2, and then this picks up a hydrogen from the HBr, and you make succinimide side product. Okay, so now we have Br2, but we have very small concentrations of it, and now the mechanism is just a typical free radical mechanism. So light or heat that will break the bromine-bromine bond to make two bromine radicals, and then the bromine radical abstracts a hydrogen atom from the allylic position, right, to make these two allylic free radicals. And then of course you can draw a resonant structure of that, so we can take one electron from here, one there, and put one there, so that will be your two allylic free radicals, and then either of those could react with another molecule of Br2. So you make the two bromo, or that would be 3-bromo-butene, or you could add the bromine to this first carbon. Right, so that'd be how your two products formed, and then in both cases you make more bromine radical, which just feeds back into this chain reaction. Right, so in theory, you only needed one NBS to break down to make Br2 to get this reaction going, and then it can self-propagate itself, but you would need more than one NBS because there's possible termination steps in here as well, right? So that's the basic mechanism, how NBS works. but you just want to basically keep in mind how to predict the product. Whenever you see MBS, just do a free radical bromination at the most stable place to put a free radical. So if we took this molecule with MBS, so this is just going to take a hydrogen off. Put bromine on, right? That's the mechanism. Fairly detailed mechanism. Predicting the product though is easy. Take hydrogen off, put bromine on. Wherever the best place is to put a free radical, which would be right there, right? Because that's tertiary and then Lilic. So your major product here would be that. And you can do the same thing with a benzylic position as well. So if you take this molecule, the best place to put a radical is right there because that's secondary and benzylic. So all MBS is going to do is a free radical bromination. And that would be your major organic product. And in both of these, you would make this like cinnamide side product that you would have to deal with, but that's easy to deal with because it's not soluble in carbon tetrachloride, so you just filter it off when the reaction's over. Evaporate off the carbon tetrachloride, and you have your products. Okay, we'll stop there.